today. Great. And that is Dr. Laura Taalman, who is a professor of mathematics at James Madison University. And so alongside her research in algebraic geometry, Dr. Taalman is an accomplished computational designer and is famous for making marvelous mathematical objects designed for 3D printing. Taalman is widely known in the math sphere of social media as Math Girl, GRRL, and has hundreds of objects featured on Thingiverse and Shapeways under this handle. And Dr. Taalman's work has been featured in art exhibitions, on the cover of the notices, and recently they were the featured speaker at the closing session of the Bridges Math Art Conference. And they're also bringing a guest, Roger Antonsen. So I'm really excited to hear this final talk. It sounds like we've got the recording going. So take it away, Dr. Taalman.
Okay, I'm going to attempt to share my screen now. Can you hear me? Can people hear me?
Yes.
Yes.
Okay, good. You should be looking at, it says mathematical technocraft. Did that work?
Yes.
Technology. Okay, great. Let me start my little timer here. Okay, so thank you so much for letting me speak in this seminar. I'm really excited about this. Is extraordinarily similar to the talk that I gave at Bridges. So if you were at Bridges, I apologize for the repetition. What I want to talk about, well, before I get to that, actually, I have a small advertisement. So the Illustrating Mathematics group has applied to do a summer session at ICERM that's kind of a reunion and kind of an expansion into new communities. And if you follow this QR code or this link, there's a web form where you can sign up to get on our mailing list so that if the session is approved, we can let you know so that you can apply to go to it. Okay, so if you have any interest at all in that, then please grab that QR code right there or that link, and maybe somebody can put that link in the Discord chat or the chat also. Okay, so what I want to talk about is the intersection between math, technology, and crafting. And I'm just going to be perfectly honest with you. I don't think I'm really good at any of these three things. Like, they're all really hard. Like, everybody knows math is hard. Doing a craft, like, it actually takes physical skill, like with your actual hands, which is like crazy. And then it takes a really long time to implement. And, you know, don't get me started about technology. Like, a lot of things can go wrong with technology. But when the sun is shining on you and things are working, you know, once you nail down the technology, it's repeatable, right? You can now make a lot of copies of something that you figured out. Once you know how to do a craft, it actually becomes something fun that you do, like, as a hobby. And also you get to, like, have stuff, like nice things that you made. And for me, the whole design process comes from mathematics, like, but the ideas of, like, how to structure things comes from mathematical structures. So if I can get in the middle of this diagram, I'm really happy. Sometimes I'm in, like, the intersection of two of these, but I'm always aiming for that middle part. So I want to tell you about this in 4 acts. Okay, Act 1 is knots that roll around. Okay, so this is a project that I did with my colleague Steve Lucas here at JMU, and a student who, at the time she began with us, was a freshman undergraduate math major here at JMU. But the project actually started about a year before that, when I got my first and still favorite printer, which is this MakerBot Replicator 2. And some students and I were producing all of these models of knots in both sort of standard and interesting illustrative conformations. And one of the students said, you know, it really is a pain that to print these knots, we have to orient them in the slicer to get 3 points to hit the build platform so that the knot is stable when we print it. And it's really hard to, like, get that to work out, you know, by hand in the slicer. So we should write some software that automatically orients our knots and identifies, like, a tri-tangent plane and puts it down. And a colleague of mine, when I was talking about it with him, said, well, did you know that there are some knots that can't be done for? And I said, no, I did not know that, actually. And he sent me a paper. And the paper was by Morton, and it's a paper from the early 90s. And in this paper, Morton proved that there is the 1 parameter family of trefoil knots that are tritangentless. They don't have any place. There's no subset of 3 points, even going through the interior of the knot, that are all tangent to the same plane. And he even had equations for that family. But honestly, he didn't have any pictures, like not even like on paper, and certainly not a physical model. So we decided to make these. And here's what they look like. Here's one rolling. You can see that it rolls because there's never a place. I'll just play that again. There's maybe, I don't know if I can play it again. I can. There's never a place where it suddenly is standing stably on 3 points, and so it just keeps rolling. Now we optimize these equations so that the knots would roll the most efficiently. And with that student, we actually wrote a paper that got published in Bridges in 2000. So for each member of that one parameter family, we found a way to stretch the knot that minimizes like kind of how the center of mass moves up and down. And you can see them rolling here. This is just 4 examples from the one parameter family. Each is optimized for rolling. They all roll well, but you have to line them up right or they fall off. But you can see that they like rock back and forth in different ways, but the center of mass for each of them in terms of height is staying relatively stable. Okay, so that's nice, but how the heck did we make the physical models that we were just talking about? Well, we made them in OpenSCAD, which you can do either very simply, like right here on the screen. This code is the complete code for making this closed curve in space. It's just taking convex hull of successive spheres along the data points of the curve. You can also be more clever, and you can use, lots of calculus and, differential geometry following around the knot, and then create like a quad mesh as you go. So you have one like really nice surface for 3D printing. You can do that too. And both of those files are in the first link on this slide right here. So if you also like to make 3D prints of closed curves in space, then go to this first link right here, and then there's a link to those files where you can then make those. Or you could just download these knots from Thingiverse, and then you could print them yourself. Or if you don't have a printer, you can order them from Shapeways, which is actually quite nice because it's very accurate and finely printed if you order from a service. When you print with a regular desktop printer, they're a little bit jagged and you have to clean them up a little bit, but they're nice. But one thing that happens is that your printer might not be working correctly. So when I tried to make a whole lot of these over the summer for Bridges, this is an actual list of what happened to me when I was trying to print them, right? Like all of these things went wrong, or I was trying to troubleshoot to get my printer to work right. And in the end, what happened is the whole nozzle was just completely burned out. And in fact, the heater block, there was something wrong with it, and that temperature sensor thingy wasn't attached right, and the set screw was stripped. It was like, it's a really old printer. So anyway, I wanted to point out that behind the scenes, there's all this stuff going on when people try to work in the intersection of math and tech and craft. And this design process that we go through is very similar to the process of doing mathematics itself. And I'll just go through this really quickly, this process. Usually you start by failing, probably twice. Okay, so you try it, it's not working out. You try more things, also doesn't work out. You try more things, also doesn't work out, right? This is like the design process and the math theorem proving process, I think. And eventually you say, well, I think that if I just keep going at this last thing, I'll get it, and you do. Okay, so you hack away at this last thing, and then you get the idea, and now you have a path from your idea to success, and you never ever speak of the failure again, right? You just erase it. You go to Instagram and you post your photos, you post it on Thingiverse, you write a paper, you come give a talk about it, whatever it is. And you don't talk about the failure, but I am going to talk a lot about failure in this talk because that's where all the interesting stuff is. And we actually want to spend as much time in this fail space as possible. In 3D printing, they call it rapid prototyping. And that just means fail fast. You want to fail fast and often, and try a lot of things. And 3D printing is great for this because you can try a whole lot of design ideas and then iterate from those. Okay. But what isn't fast is knitting. Knitting is not fast at all. Knitting is very, very slow. Knitting and crochet are both very slow processes that you are doing as the human with your actual hands. And so just as an example, here is a video of me crocheting. I'm not a particularly fast or slow crocheter. It's like 3 stitches a second or something. Oh, I don't know what I said. 10 stitches, oh, like 20 stitches a minute, right? This particular thing that I'm making is just a small throw for a sofa. And it has about 21,000 stitches in it, which at my rate of stitching should take 18 hours. So like if I was a crochet machine and you just set me to work at it, I didn't have to eat or sleep or stop, and I didn't make any mistakes, it would take 18 hours. Now this is, honestly, this was an incredible fact to me when I did this calculation, because the amount of time it actually took me was 1 year. It took me 1 year to make this blanket because I would knit through some colors and I didn't like them, and then I would have to go back. I would discover I made a mistake on the edge and I would have to go back. I would get angry and put it away and not look at it for 3 weeks at a time. Like, it really took a long time. This is not a good iterative failure design space here. So how do we fix that? Well, there is no such thing as a crochet machine, but there is a thing called a knitting machine. And I hope this isn't too loud, but I wanted you to be able to hear the sound that it makes here. So this is a knitting machine. Every time I go back and forth is 20 stitches. So 20 knit stitches, 40, 60, 80, 100 stitches. This thing is just cranking out stitches. This is a machine from the 1980s. And hold on, it's sometimes hard to make the video stop. Okay, this is a machine from the 1980s. It has no electronics on it whatsoever. Instead of, when you knit, you have 2 needles and you're manipulating loops of yarn that are staying on these 2 needles. In the case of the knitting machine, you have 100 or 200 needles on the top bed and possibly another 100 or 200 on the bottom bed. And each of those needles is a little hook holding its own individual loop of yarn. And so that's what this is showing right here, are those loops being captured by those hooks. The yarn goes down through this carriage that you saw me moving back and forth. And then the bottom of the carriage looks like this. The needles go through the carriage, through this mechanism, and they do a process that is kind of like what I've shown in this picture here to make a new line of loops connected to the previous line of loops. So like I said, this is the analog technology, like non-electronic technology from like 1984. And there is a lot of space for things to go wrong. A lot of things can go wrong here with the carriage, or, you know, this is what the instruction manual looks like when you're working with it. I mean, there's a lot of stuff going on with this weird machine that can happen to you. But if you're lucky, you have now made a knit tube. So in that video, I was actually knitting a tube in a circle. And so now I have the capacity and the workflow to create long knitted tubes of fabric. So why would I want to make long knitted tubes of fabric? Well, the answer, of course, is because I was interested in finding out what would happen if I stitched all those tubes together, because sometimes they fall off the machine in the middle and they're not so long and you have to fix it. And then I stuffed them with stuffing like a teddy bear and made knots, like giant knots. Like, so these knots are like big huggable knots. As you can tell from the banana there, they're pretty big. So I wanted to make knots like this specifically because I was interested in minimum rope length conformations of knots and how to realize those in a way that you could really sort of appreciate the structure of what was happening. I managed to convince someone to publish this paper, which I think is really great. And the paper tells you, using known results about minimum rope length of knots, how long a tube you have to knit to make particular knots based on your gauge and how the machine works and things like that. And so, for example, I knit this minimum rope length conformation of 10, 1, 20 I think this one is based on Jason Cantarella's minimum rope length data. And I knew exactly how long of a tube I had to knit to be able to make this exact conformation of this exact knot. Here's another example. Here is the Borromean rings. So this is three, let me show you a different picture. It's three circles that no two are linked, but altogether the whole thing is linked. Although this is the picture in Wikipedia, this illustration here, it is a lie, because it turns out there's another paper that surprisingly shows that Borromean rings cannot be made of circles. I think that's actually the title of the paper, Borromean rings cannot be made of circles. And if you have this large huggable model, it's immediately clear why they can't be circles, why they have to be kind of ovals to pull off the type of over-unders that happen with this. Okay, so this is great. Okay, so now I have this nice workflow. I don't have a crochet machine, but I have a knitting machine, so I can make knit things quickly and play around in that space. But honestly, it's kind of ugly. Like these pieces, when I knit them on the machine, had these weird artifacts. Like the green one is great. This yarn is called Impeccable Speckle. The green one is killing it. It's great. But the blue one and the red one, like I'm getting stripes and weird stuff. And why is that happening? Well, the yarn has these little speckle pops of color at semi-regular intervals. And depending on like whether it's Tuesday and how your machine is set up and the tension of your machine, you might hit that, that regular pattern in a way that is ugly. Okay. Here's an example with a yarn that is made to make stripes. And so you can see this yarn is light blue for a while, and then dark blue for a while, and then kind of medium blue for a while. And here's a piece I crocheted. It's like about this big. It's like a 12 by 12 square using this yarn. And I mean, it worked. I can do it, but it is very ugly. Okay, like this is not stripes. This is not what you would want to, like, you don't want this sweater. Okay, so what is happening? Well, when you are crocheting with this yarn, you tend to do about 10 dark stitches, and then 5 of the white stitches and 4 of the medium stitches, like give or take a stitch here or there. That's about how it shakes out with that yarn. So you're doing 10, 5, 4, 10, 5, 4, 10, 5, 4 over and over. And when you wrap around to come the other way, you're still doing 10, 5, 4, 10, 5, 4, 10, 5, 4, da, 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 da. Okay. So you're doing this pattern, and that's what's causing these like weird artifacts to happen in your design. It's like how these things happen to line up. So I wanted to investigate this. This is a known thing called color pooling that happens with knit and crochet in a variegated yarn. And sometimes it's pretty and sometimes it's ugly. So I made an app so that I could predict whether it was going to be pretty or ugly, because like I said, crocheting itself takes a really long time. So here is an app. I wrote this in P5. It's online right now. And you can see at the bottom, I've got 10, 5, 4. That is the stitches. If you look, I think you can see my mouse, right? I've got 10 stitches here, starting from the lower right corner, and then 5 of the light blue stitches, and then 4 of the dark blue stitches, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 should be 10 stitches. I hope it's 10. Oh, it goes here. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these. And then 5, they're kind of interlaced because that's how this this is the moss stitch in crochet. And the whole piece is 26 stitches long. Okay. And you can see that this really does match what happened to me in reality when I made this thing. And if I go forward a little, I can now see what if instead of 26 stitches, I use 25, and I don't have to spend an afternoon crocheting it up to see what happens. I can just look. What if it's 35? What if it's 36? What if it's 38? Now, this is kind of surprising because remember, I'm just using one color of yarn here and I'm just crocheting back and forth. But 10 plus 5 plus 4 is 19, and 38 is twice 19. So I'm really just doing all 19 and then all 19, and then I'm going the other way and doing all 19 and all 19, and then every other pair of rows after that is identically the same. So this is It's kind of cool that you can make a vertically striped yarn by crocheting horizontally, but it is also very ugly and I would avoid this. Here's a 60. If I made a 60 across, you can see we're starting to get something interesting happening. 52, starting to get interesting. 33 is kind of like a zoomed in version of 32. But check this out. This is 28. If I did 28 stitches with this piece of yarn that's changing color at fixed intervals, back and forth, this is the pattern that I get. I did 26 stitches in my sample. I was just off by 2. If I had just made 2 more stitches across, I would have had this sweater instead of the ugly sweater. And it actually works. Like here, then after doing this, I went and did it and it actually works. So if you make sure you obey 10-5-4 the whole way across, which if you're a knitter or a crocheter, you know that the number one thing you have to do is keep an even tension. And you have to disobey that to make this, because you have to change your tension to ensure that you're doing 10-5-4 all the time. And so you end up crocheting for a while, and then you end up only getting 9 stitches instead of 10. So you have to rip them all out and make them all slightly tighter so you actually get 10. Okay, it's really a pain. And the yarn, when it's manufactured, isn't identically long intervals. And so you're also making up for defects in the yarn. But if you can keep to 10-5-4, then this is what you get. Okay, so here is some more things from the app. Like there are yarns that are made to do crochet color pooling, but these are all fictional yarns. Okay, so I made up at the bottom, you can see the color sequences and how long, how many stitches they last for. And this is just going through, this app is really fun. If you go there and just press the lowercase r, then you get all these different random color patterns. And then if you get a color pattern you like, you can press F to F it up a little and then change how the colors move. Okay. Now, I actually am working right now on, I want to write a paper about why these come out nicely and others come out bad. Like this is the good ones and the fails I didn't put in this picture, okay? And I don't think it's that hard of a problem. I don't think it will take very long. We're sort of started already. And if you are a JMU student watching this talk right now, please come see me about applying for the student research position I have to do this, because I want to write a paper with you, and then maybe we'll get to go to Bridges and present this paper, okay? If you want to just play around with the app, here is a QR code that goes to it, but it doesn't work very well on your phone. So weirdly, if you capture this QR code, you should then email it to yourself and then open it on your computer later or whatever, or you can just go to that link. So you can play around with it there and make all kinds of cool patterns. Okay, so great, fine. So now we can fail somewhat faster in the crochet space, which is nice. Act 3, I want to talk about expanding what we can do with knitting machines and with patterning. And this is work that I've done with Carolyn Yackel and also with Roger Antonsen. But first, the knitting machine. It turns out it can do more than just knit hollow tubes of fabric, right? As you might expect, nobody really wants those. It can knit multicolored things. So this is actually a 2-color knit here. One of the colors of yarn itself changes color, so it looks like it's a lot of colors, but it's black yarn and then the other yarn, okay? And that punch card that you can see in the background there, that's actually determining the pattern that's coming out on here. Here's how that works. So first you have to punch a card. Okay, so you can get a hole puncher like this that's specially made to punch these knitting machine punch cards in a pattern. You can also use some kind of, Silhouette Cameo or this Cricut Joy, and then have a digital file that you send to have cut the holes itself. That sounds easier, but it's actually not easier. It's so much faster just to punch the card. So once you do it either way, though, you end up with this card with all these nice holes in it, and then you put the card in the machine. You can see it in the back there, And that card interacts with a belt that's going along the machine behind the metallic part of the bed. And that belt is interacting with the carriage, which then pre-selects which needles are going to get pushed out farther. If you look closely, you can see that some needles are pushed out farther than others. And then you put 2 yarns through the carriage. And when you move the carriage across the next time, it chooses which yarn to use based on which yarn is forward or back. Okay, this is a really cool feature that the knitting machine can do. And so now it's a pattern making machine. Like we can make cool patterns, which means, so here's an example, just a sample of showing that you can knit, and then you can very quickly, if you get everything else set up correctly, make this a reproducible way of producing this pattern. Of course, behind that success is a lot of failure and trial and error to try to get your stupid little holes to line up in the stupid little boxes. And there's tiny little punched holes all over your floor and your clothes that came out of your punch cards, and you have to write some code. And then the machine itself needs to be in alignment. And then, you know, you do it backwards for some reason. This last picture, you can see I'm wearing a Band-Aid because I literally got injured while the process was happening. Like a lot is going on to do this. But once you settle it, you can make these nice things. So step 4, what are we going to do with that? Okay, so now we have the ability to make like replicable patterns in knit fabric. What should we do with it? And Carolyn Yackel and I started working on a project related to this that is for making wallpaper patterns for lattice designs. Okay, so famously, there are 17 wallpaper patterns that have different symmetries that you can measure. We have a more restricted universe where we're taking a tile and flipping and rotating and mirroring and translating it around to achieve certain wallpaper symmetries. We count some vertical and horizontal things separately that would have been counted the same, you know, if you're just looking at the 17 wallpaper patterns here on the left. But we published a paper about this, and the paper was really about an app that we made. And this app takes a tiny tile. You can see this little smiley pirate in the corner, and it flips and rotates that tile around to make different wallpaper symmetries. You can see we're going down the list here in this rainbow, and then it's showing you the glide and mirror and other symmetries that are in each of these patterns. And so from one small tile, you can get a large collection of patterns. Okay, and I think if I let this go long enough, it will actually also show multicolored patterns. Let me just wait. I think, yeah. So you also can do 2-color wallpaper patterns where the 2 coloring obeys the wallpaper symmetries in very particular ways. And different wallpaper symmetries have different options for that. We also made it look like punch cards so that if you were thinking about making punch cards or knitting, it could look like that. That's what we call punch mode. And in fact, we made a little entry screen here. You can see these punches so that you can literally punch the holes on the screen, and then it would make the wallpaper pattern that you have selected in the little rainbow here. And then once you have your punched little tile, you can look at all the different things you can generate with that tile. And it is a surprising amount of things that you can generate just from one little tile, especially when you start adding all the different colors and things. But you still have to then somehow get the design onto a punch card and put it in the software for punch cards and get it cut and this whole thing, right? So we made that. It's not available online yet, but we're working on making it available online, so you can maybe use it in an abstract algebra class or something if you wanted to explore wallpaper symmetries. This led directly a year or two later to Roger and I writing an online app called Pattern Punch Knit, which is online right now at patternpunchnit.com, that's specifically made for punch card knitting machines. So with this, it's kind of like symmetry generator, where you have a particular pattern that you're starting with, and then the wallpaper symmetries generate larger patterns, but they're all based on a 24x60 punch card. So it's really putting the pattern on the punch card and then putting the punch card to the larger visualizer here. And you, again, can get a surprising amount of patterns just from that P, but then also you can make random patterns in the original pattern that then has a random wallpaper group for the punch card and then makes a fabric, and you can preview the fabric so you don't have to injure yourself making it. You can imagine what it's going to be like. You can press like there's a crazy button you can press that makes even crazier things. And it's a huge amount of patterns. And if you've ever used a punch card knitting machine, it comes with like 13 punch cards, and you see them on people's sweaters everywhere, right? Because these are the punch cards people have. And so we really wanted to increase like sort of the variety of punch cards that are out there. Okay. All right. It also gives you these little warnings if you do something that makes an ugly pattern. So it knows about the punch card, it knows about the size of the punch card. And then we made a gallery where you can actually look at saved designs that you and other people made. So here's some of the things that users came to Pattern Punch Knit and made. I mean, honestly, Roger and I are the majority of those users, but there are other people that go here and make these patterns, which I think is really exciting. And we come back and there's like fun patterns have been added to the gallery that people made, and people get pretty creative. And each of these you can click on and then you're in the maker again with that pattern. Okay, here is the link if you want to go and play with this. Once again, you can do it online, but it's really not made to use on your phone. It's made to work on your desktop. There's a lot of screen real estate you need to do this well. So if you want to play around with that, you can go here. Okay, but probably not too many people are trying to make punch cards for their vintage punch card knitting machine from the 1980s. So Roger and I started thinking, well, maybe we should think more broadly, right? More broadly past wallpaper patterns, patterning in general, and not be tied to the 24x60 punch cards so much. And so we consider Pattern Punch Knit done, and you can export directly to files that you can punch on that Silhouette Cameo or whatever you have. But we started a bigger project that we call Stitch Wizard. Okay, so this is a project that we've been working on, Roger, I think we've been working on these two projects for years, for a long time. Yeah, we work on these often and for a long time. And I'm so happy that Roger is here right now because he is actually going to be the special guest star of this talk. And I am going to stop sharing my screen and Roger is going to take it from here. So let me unshare so that Roger can take over.
Okay, hi. Thank you for that. Yes, we have been working on making knitting patterns, but working in those specific dimensions were kind of limiting. So this came out of need. So we present to you the Stitch Wizard, designed by Phil Riley, and he has a knitting pin. Is that what it's called? Yeah, as his wand, and he actually knitted himself. This is a miracle, and he is now here to help us make knitting patterns. So the app looks like this. It's called stitchwizard.app, and you can find it online. And this will be the successor of the previous app. So the idea is that you start with a pattern on the left. So if you can see my screen, I'm clicking on the left, and I get a knitting pattern on the right. So then we thought, why don't we take the most general approach that we can find, which is, take a grid and transform it into some other grid by any function. And then we started playing with the metaphor of casting spells. And it was perfect because what do the wizard do? The wizard casts spells. And what are spells? They're functions. They're functions that take grids and they return grids. So I'm going to add a spell, and the spell is multiply. It's the simplest of spells. So what does it do? It just copies. It just creates vertical and horizontal copies or whatever you put in. Now you can put in something else, and the goal here is to have something that's reactive that you can work with from all directions. So I'm going to show you some of these spells. This is just for fun. This is gravity. What it means is that things fall to the ground. If you want them to fall up, that's okay. We make them fall up because gravity works always. or left or right. Now, that's one example. And we also put in the wallpaper stuff from before. So if I put in, let's say, the letter P, I can do here various kinds of things like this. We can also copy this away more. So the idea here is that I can cast spells, and I can choose which ones. I can pause them. I can, reorder them. So let's see an example of this reorder thing. So if I do gravity after I do wallpaper, they all fall to the ground. But if I do gravity before I do wallpaper, I get this. And you can get sort of very surprising effects just by this little, by very, very small variations. And we have had so much fun with this, and we don't know exactly where it's going. We are going to make this thing here more, so you can choose more colors, and you can sort of design and export and import and all that. And I want to show off some other spells. You might recognize this little thing. Of course, I mean, what are we going to put in? What are the spells that takes a grid and transforms the grid to another grid? Well, Game of Life. Okay, let's try Game of Life. So here I can step through Game of Life. So I've created a glider. So I've told the system to wrap, otherwise it would, stop and die there in the corner. So we're going to go for wrapping, and I'm just going to keep this animated for now. So what I can do, I can add, while it's running, another thing on top of it. So let's add wallpaper. Now, doing wallpaper after might be a good idea, might be a bad idea, but here's a kind of cool effect. I'm going to stop the animation for a second, and I'm going to move the wallpaper to the top. And first of all, I'm just going to copy this. So I get a bunch of copies. Let's do 8x8 gliders. Now, what's going to happen when I start them? They're all going to walk, and they're all going to walk like in perfect order. And now comes something else that we realized that was really fun. If you do a horizontal, if you flip vertically in the horizontal direction and you rotate in this direction, there's probably a fancy name for this, you get this. And here you see a bunch of gliders, 64 actually, that never crash. I've never seen this before, and I was so delighted. What's going on here? We started out creating an app for creating knitting patterns, and I think we got something entirely different. So and we got that, and we got more. So now, of course, I can add stuff to this. If I add gravity at the end, we get this weird wonky thing going on there. I'm not really sure what it's doing. So here we have a bunch of freedom to do whatever we set out to do, and more. Did I forget anything? I think this is a quick demo of something that is work in progress.
Wave.
Oh, yes, thank you. I knew there was something. Okay, so there is a particular way to create patterns that we sort of, we wanted to have in here. We have it in the pattern punch knit too. It's something we call wave. It's called wave, function wave collapse. It got very popular a few years back, where you use a metaphor from quantum physics. But it was known before as model synthesis, and it's basically constraint solving. Or Sudoku. You attempt to satisfy some constraints. So it works like this. So if I draw a little square like this, I get a bunch of squares in my pattern. So the rule is now that every 3x3 on the right must come from a 3x3 on the left. And those are the constraints. So when the system starts, it really just maps out all 3x3 possibilities and calls them tiles. And then you use those to try to tile the entire plane. And you do that sort of randomly. If you have several options for what to do and where to go, you pick randomly from the best of your options. Now that process might crash and you might not succeed. Here are some examples of this. And if you do a 2x2 instead, you restrict the space a little more, or a 4x4, you get different results. So here's another one with just diagonals that is really good for 3x3. So you get all these strange things. But if you try 2x2, it sort of all looks the same. But for 3x3, it really works. And also, if you put in a little bit more, this will very quickly get unsatisfiable. And you can do a lot of work with this. We run it just once, and if it's unsatisfiable, we don't backtrack or try again. We just show you the result. For that particular seed, it did not go through, but for this one it did. So we think this is really fun. And the idea is to take a pattern that many people know and create variations of it that sort of has the same characteristic as the original one, but sort of is new. So as a tool for creating new patterns. So yeah, we look forward to working more on this and sort of explore what we can do, and build out this metaphor of casting spells. Because this, if you talk about math communication and sort of how you talk about math in public, this is also a thing. I mean, it's a very friendly thing to talk about, but under the hood, you're really talking about applying functions. So anyway, I think that was it.
Thank you. There were two questions in the Q&A that I would love to sort of bounce to you before we say our goodbyes. The first was a question that asks, do you know if there's been any anthropological research to find out how traditional weavers and crocheters figured out how many stitches to use?
I assume that's about the crochet color pooling, and the typical thing that people do is they take the sum of, like, well, we had 19, the sum of those colors, and they add 1, and if that doesn't work well, they subtract 1. Now, how they discovered it in the first place, I don't know, and I would like to know that, because I didn't make up crochet color pooling. That is like a thing that already exists. But if you go and watch YouTube videos about it, it's really like a lot of trial and error. Like, a lot of people are like, let's try to add 1, and then they do it for like 5 rows and they don't like it and they start it again. And so there's already another app that does what my app does, and now there's 2 apps where you can go and actually plan it. But I think that we're going to find formulas for it that in that research project. Hopefully the undergraduate will do that. But no, I would love to know the history of that, and maybe that's something else the undergraduate student working with me can think about.
Awesome. The same asker actually asked as well, can one create images with your app, which would be a step up from producing patterns?
Which app was that they were talking about?
I didn't see exactly when this was posted.
Maybe that's a more of a Stitch Wizard question.
I think it was posted before Stitch Wizard, but I think Stitch Wizard might answer that.
We do, and in Pattern Punch Knit, because of the gallery, we have a way that you can get out the images, but the images are, of course, of either knit stitches or little squares, right? So, but Roger, I don't know if you want to say something more about that.
No, that's fine. We intend to have all sorts of ways to output these into images, SVGs, PNGs, whatever you want. And, even have users and all that stuff, so you can store your favorite patterns and share them.
Terrific. And Nicola gave a fun suggestion that just said that they love the spell casting and casting on and casting off and knitting. And immediately it looks like it would be great for a stop motion project with the glider creating patterns for sweaters that move when different sweaters are warm in different frames, which is a awesome suggestion in my mind. If you've got a lot of time on your hands, I love. If there are any other questions, you can post them in the Q&A or raise your hand, or just post them in the Discord and have that continue after.
I see one in the Discord right now. Can I answer it?
Mm-hmm.
It says, does minimum rope length give a good estimate for huggable knot tube length right out of the box, or do you have to do some correction or trial and error? This is a very good estimation, but you have to know, like, the gauge and stretchiness of your particular yarn and your particular machine settings and all that sort of thing. But the estimate is spot on. Having said that, the formula also includes a relaxation factor, so you can make them there so they're not like, so they're actually not minimum, they're minimum-y. So in that context, it's even a better estimate because it's really loose estimate. Yeah.
All right. Well, thanks to all our speakers, wonderful presentations, and thanks to everyone for coming. And please feel free to continue on the Discord channel, please feel free to check out our illustratingmath.org website, which I just put in the chat. And please come again next month. We expect to be at our usual time, which is an hour earlier than we met today. So noon if you're in the US Eastern time zone. That's our usual time, and it was not our time today, but we'll be back at that time next month, featuring Henry Segerman, and hope to see you all there, if not sooner.
Thank you.